I want you to think, just for a second, about the number 5.
Just the number itself.
Right. Just picture it in your head, like 5 smooth stones sitting in the palm of your hand.
Or maybe 5 meters of distance you have to walk across a room.
Exactly. Or, 5 units of thermal energy trapped inside a closed system.
Yeah.
Because ever since we were kids, right, sitting in our very first math classes, tracing those numbers on lined paper, we have been taught this very specific, unquestioned rule.
A fundamental assumption, really.
We've been taught that a number is what you might call, well, context-free.
It's the ultimate plug-and-play tool.
The absolute abstract ideal. I mean, you take that number 5, you pick it up out of your hand, you carry it anywhere in the universe, you plug it into literally any equation, and it absolutely does not change what it is.
5 is always 5.
Right. It is clean, it is perfect, it's completely universal, and as a foundation for understanding reality, it feels, incredibly solid.
It brings a sense of deep comfort, honestly.
Yeah.
We've built our entire technological civilization on this.
Like our architecture, right?
Architecture, classical physics, the global economy, all of it sits on that foundational assumption. We assume that quantity is fundamentally detached from the messy, chaotic reality of the physical world.
And here's the paradigm shift we're exploring today on this deep dive, and it is a massive one.
It really is.
When you step out of that clean, perfectly abstract classroom, and you step into the messy, incredibly complex reality of modern physics or living biology or even advanced artificial intelligence.
That pristine abstraction, it's actually a lie.
It's a total lie. Magnitude alone, just asking the simple question of how much, is fundamentally, as our source material today puts it, ontologically insufficient.
Which is a heavy phrase, but it means a lot.
Yeah, basically you simply cannot detach a value in a system where that value depends entirely on what direction it's moving, or what microscopic or macroscopic scale you're looking at it from.
Or the specific structural symmetries it has to stubbornly preserve just to keep existing. When you strip away all of that context, in the name of making the math easier to write down, you aren't just simplifying reality.
No, you're actively destroying it.
Exactly. You are destroying the very information that defines what that reality is. You're blinding yourself to how the system actually behaves.
And that brings us to the mission of this deep dive. Today, we are immersing ourselves in a truly revolutionary 2026 paper by Philip Lilien.
The Noetherian Finsler numbers paper.
Yes, Noetherian Finsler numbers, or NFNs for short. Over the course of this deep dive, we are going to comprehensively explore what Lilien calls a new calculus of closure memory.
Calculus of closure memory. It's such a poetic way to frame it.
It really is. Now, I want to be very clear right up front for anyone listening who might be feeling, a little math anxiety.
But don't panic.
Right, don't panic. This is not about throwing out standard mathematics. We aren't tossing out real numbers or complex numbers or the things you learned in high school geometry.
Far from it, yeah. This is about establishing a higher order language for numbers that actually remember the conditions under which they remain themselves.
That remember what they are.
Right. We are talking about a formal, structural mathematical language for tracking how reality persists under intense transformation.
A number with memory. I just love the sound of that, because we aren't talking about abstract equations scribbled on a dusty chalkboard just for the sake of theory.
No, the applications are incredibly tangible.
We're looking at a mathematical framework that models how a living, breathing biological cell stays a living cell while constantly exchanging matter with its environment.
Or how a massive turbulent hurricane holds its structure together across thousands of miles of ocean.
Exactly. We're even looking at how fragile quantum states survive shifting symmetries without just, collapsing.
The stakes here are incredibly high because our current mathematical tools are hitting a wall.
A hard wall.
Yeah, we have reached the absolute limits of what a context-free number can describe in our universe.
So let's start right there. Let's look at that wall, because to really understand why we desperately need these Noetherian Finsler numbers, we first have to understand exactly where our standard, everyday numbers fail us in the real world.
And they fail in some surprisingly common places.
They do. Think about it for a second. What actually happens when a physical quantity changes entirely depending on the direction you measure it?
In physics, they call this anisotropic media.
Okay, let's unpack this. The classic everyday example I always think of is a piece of wood.
Oh, well, it's a perfect example.
Right. The structural strength of a piece of wood is completely different depending on if you're pressing down with the grain or against the grain.
Yes, drastically different.
If you just write down, oh, this wood has a structural strength of 10, that number is entirely meaningless.
10 what? and in what direction.
Exactly.
The direction dictates the reality of the material. And you can see this in crystalline structures too, like quartz crystal.
Oh, interesting. How does that work?
Well, the way light passes through it, or the way electricity conducts through it, is highly dependent on the internal geometric axis of the crystal.
So the orientation literally changes the conductivity.
Exactly. If you just assign a simple magnitude, a standard scalar number, to the conductivity of quartz, you are telling an incomplete story. You're lying to yourself.
Wow. And it goes beyond just direction, right? What happens when something behaves one specific way at a microscopic molecular scale, but operates under totally different mechanics at a massive cosmological scale?
Oh, the scale problem.
Like, you know how gravity is the absolute ruler of the universe when we're talking about planets and galaxies. But when you zoom down to the level of a single atom, gravity is so wet, it's practically non-existent compared to the strong nuclear force.
That is a brilliant example.
Hmm.
The rules of engagement completely change depending on the scale of the arena.
So asking how much just isn't enough.
No, asking how much gives you a scalar. That's your baseline number. Asking how much and in which direction gives you a vector.
Which is better.
It's better, sure. But when you are dealing with living systems or fluid dynamics or quantum coherence, neither of those questions goes far enough.
Because they're still missing context.
Right. A vector can't tell you what scale you are operating on, and it certainly can't tell you what the system is trying to preserve. You need much more scaffolding.
And Lilien's paper lays out this scaffolding beautifully through a concept he calls the reduction ladder.
Injection ladder, yes.
I found this to be one of the most illuminating parts of the source material because it really shows how we have historically built up our math. But I might need some help parsing the higher rungs here.
Let's climb it together step by step.
Okay, let's do it.
Think of this ladder not as a hierarchy of superiority, like one type of math isn't morally better than another, but as a hierarchy of retained structure.
Okay, retain structure.
So at the very bottom rung, you have the scalar.
Mhm.
That is your simple number 5. It just records pure magnitude.
Just how much, nothing else.
Yes. You step up one rung and you get complex numbers.
Which adds another layer.
Right. Now you have magnitude plus phase. You have incorporated an angle of rotation, a cyclical component.
Okay, I'm with you.
Step up another rung and you reach vectors. Now you have magnitude and a specific linear direction in space.
Those are the little arrows we all had to draw on inclined planes in high school physics, right? Pushing a block up a hill.
Exactly.
Yeah.
Everyone remembers drawing those force vectors. Then you take another step up and you reach tensors.
Tensors. This is where the math starts looking really intimidating on a chalkboard.
It does, but conceptually, tensors are incredibly powerful because they record how a quantity transforms relationally across different coordinate systems.
So they don't just point in one direction.
No, they describe the relationship between multiple directions and magnitudes simultaneously.
Right.
Einstein leaned heavily on tensors for general relativity to describe the curvature of space-time.
Okay, so up to tensors, I'm trapping, I get it. But the next step on the ladder is where I start to feel the altitude sickness.
This is where we leave standard physics behind.
Right. The paper introduces Finsler objects. What exactly are we retaining when we move up to a Finsler object?
To understand Finsler objects, we really need to talk about Finsler geometry.
Okay.
In standard geometry, the kind we usually use to map out space, like Riemannian geometry distance, is isotropic.
Meaning it's the same in all directions.
Exactly. Means a mile is a mile, regardless of which way you are facing.
Makes sense.
But in Finsler geometry, the actual shape of space, the metric distance itself, depends on the direction you're traveling.
Wait, hold on. You're saying the actual mathematical distance between me and my kitchen could change depending on which way I'm facing?
Yes.
Because conceptually, that sounds like a glitch in the matrix.
It does sound deeply counterintuitive if you think of space as an empty room. But think of space as a medium.
Okay, a medium.
Imagine you are swimming in a fast-moving river.
Right.
If you are swimming upstream against the current, the physical, energetic cost of moving 1 meter is enormous.
Yeah, you'd be exhausted.
But if you turn around and swim downstream, the energetic cost of moving that exact same physical meter is trivial.
Because the river is doing the work for you.
Exactly. The environment is anisotropic. Finsler geometry builds that current directly into the mathematical measurement of the space.
Oh, wow.
The direction you choose literally dictates the metric reality of the journey.
Okay, that makes perfect sense. The effort required is woven into the concept of distance itself.
Yes.
So that gets us to Finsler objects. What is the next rung on the ladder?
Moving up, we reach Noetherian invariants.
Named after Noether.
Yes, derived from the brilliant mathematician Noether. Her theorem essentially proved that for every continuous symmetry in nature, there's a corresponding conserved quantity.
You know, I have read a bit about Noether, and it is almost a crime how little she is talked about outside of physics departments.
It really is. Her work is the absolute bedrock of modern physics.
But for you listening who might not be familiar, what do we mean when we say a continuous symmetry?
Think of symmetry as a physical system's immunity to a specific kind of change.
Immunity to change. Okay.
So if you perform an experiment today, and you perform the exact same experiment tomorrow, the fundamental laws of physics don't change.
Right.
The system is symmetric with respect to time. Noether proved mathematically that because this time symmetry exists, something must be conserved.
And what's conserved?
In this case, it is energy. Conservation of energy exists because the laws of physics don't care what time it is.
That is mind-blowing.
And it applies to space, too. If the laws of physics don't care where you are located in space translational symmetry, then momentum is conserved.
So an Noetherian invariant captures the specific structural property that simply refuses to change when a system undergoes a transformation.
Exactly.
It's the stubborn core of the system.
That is a great way to put it. It is the architectural anchor. And that brings us, finally, to the very top of the reduction ladder.
The peak.
The culmination of all these retained structures. The NFN, the Noetherian Finsler number.
So the NFN retains all of it. Everything.
It doesn't just ask how much. It asks how much, in which direction, at what specific scale of reality, and under which stubborn invariant condition.
It refuses to drop any of the context.
You know, reading through this ladder, the analogy that kept repeating in my head is video compression.
Oh, I like that. Let's hear it.
Moving down this mathematical reduction ladder from an NFN all the way down to a basic scalar is exactly like taking a massive uncompressed, ultra-high-definition 4K video file and compressing it down into a tiny, blurry, silent GIF.
Yes.
Right. Yes, the GIF takes up way less space on your hard drive. It is incredibly easy to text to your friend.
The math is easy to write on a blackboard.
Exactly. But you lose vital, sometimes crucial information. You lose the color depth, the frame rate, the audio, the sharp edges.
I think that is the perfect way to conceptualize it. You are trading resolution for convenience.
Yeah.
And Lilien actually formalizes that exact loss of resolution mathematically in the paper.
He does.
He introduces a rigorous concept called projection cost. Wait, how do you mathematically measure the cost of ignoring reality?
He uses a specific notation, a capital K sub pi. This projection cost essentially measures the mathematical friction or the formal loss of information when you force a highly complex context-dependent reality into a simpler mathematical projection.
So when you make the GIF.
Yes. When you take a system that requires a tensor to fully describe its internal stresses, and you force it into a simple vector equation, that suppressed information doesn't just vanish peacefully.
It has to go somewhere.
Right. It manifests as a projection cost. It manifests as an error in your predictive model.
Like trying to force our wood grain strength into a simple scalar number.
Exactly.
If I just write down 10, the projection cost is the catastrophic failure of the bridge I just built because I didn't account for the direction of the load.
Precisely. The bridge collapses because the math lied to you.
That is terrifying.
And the crucial point Lilien makes is that projection isn't inherently evil. No, it is a highly useful tool. I mean, classical physics got very far by projecting complex realities down to simpler forms.
Like Newton's laws.
Exactly. If you're calculating the trajectory of a cannonball, you don't really need to calculate the biological state of the bacteria living on the iron surface.
Right, that would be overkill.
The projection cost of ignoring the bacteria is virtually zero. It doesn't affect the flight path.
Okay, I see.
The error only occurs when the components you suppressed were actually essential to the system's core behavior.
Ah.
If direction, scale, and identity matter, like they definitely do in fluid dynamics or living tissue, your projection cost spikes to infinity.
Your standard math is just going to give you a fundamentally wrong answer.
A catastrophically wrong answer.
So if standard numbers are actively suppressing all this vital context and creating massive projection costs, what does a number look like when it is built to remember everything?
It looks like a completely different beast.
Lilien takes this abstract problem and builds a physical architecture for a new kind of number. So let's put an NFN on the examination table right now and look at its anatomy.
Let's do a dissection.
Instead of just a single digit, the paper defines an NFN as a highly structured coordinate system with 4 distinct components.
Right.
Imagine unpacking a single number and finding 4 specific functional organs inside it.
The formal notation defines an NFN as a set containing M, a bold D, a capital S, and a script Q.
Okay, let's go through them. Let's start with the first organ.
This stands for magnitude.
Okay, this is the familiar territory, right? The intensity, the density, the sheer amplitude of whatever we are measuring.
It is familiar, yeah.
Yeah.
But the critical difference here is that in the NFN framework, M is no longer isolated.
What do you mean?
It is entirely tethered. You cannot extract the magnitude and play with it on its own. Its literal value is completely dependent on the other 3 organs.
So it's not just 5, it's 5, but only under these 3 specific conditions.
Yes.
Okay, and the first of those conditions is the bold D, which stands for directionality.
Right.
We touched on this with Finsler space, but how does this actually function inside the number itself?
The bold D acts as an orientation lock.
Orientation lock.
Going back to our river analogy,
Mhm.
if your magnitude is your swimming effort, the D explicitly binds that effort to the flow of the environment.
So it knows which way you're pointing.
Exactly. If the D changes from upstream to downstream, the functional output of the M dynamically changes without the M itself having to be rewritten.
Oh, wow.
The number is aware of its posture in space.
It's aware of its posture. I really like that phrasing. So we have magnitude tethered to directionality. The third component is the capital S, which Lilien calls the scale, or the closure regime.
The closure regime, yes.
And I have to admit, when I read this section of the source material, it forced me to completely reevaluate how I think about physics.
It's a huge conceptual leap.
It is formalizing the idea that a mathematical value that is profoundly meaningful at the quantum scale might be complete, literal gibberish at the planetary scale.
It is a radical shift in perspective. Because historically, human observers have treated scale as an arbitrary external choice.
Just how we look at things.
Right. Scale is just a dial on our microscope or a telescope.
Yeah.
We decide how far we want to zoom in, and we assume the math just scales linearly up and down forever.
Because math is supposed to be universal.
But Lilien argues that in highly complex systems, scale is not just a human viewing preference. It is a physical, bounded reality of the system itself.
Can you give an example of that? Because it feels like if I have one atom, I can just multiply it by a twillion and get a rock.
Let's look at weather.
Okay.
Let's look at a turbulent eddy, a swirling vortex of air in a larger storm system.
Like a mini tornado inside a hurricane.
Exactly. That eddy operates at a very specific atmospheric scale.
Hmm.
The thermodynamics, the friction, the velocity, they're all locked to the physical size of that vortex.
Right. It has physical dimensions.
If you mathematically try to shrink that eddy down to the size of a single molecule, the fluid dynamics completely break down.
Because molecules don't have swirling weather.
Exactly.
Yeah.
The physics of the eddy do not exist at the molecular scale.
Oh, I see.
The NFN uses the S component to mathematically lock the value to its appropriate regime.
So S acts as a boundary.
Yes. If an equation attempts to pull that NFN out of its closure regime, the math outputs a null state. It rejects it. It protects the reality of the phenomenon.
It prevents you from doing mathematically legal but physically impossible things.
Precisely.
That is amazing. So we have magnitude, direction, and scale. Now for the fourth organ, the real heart of the NFN.
The script Q.
The conserved invariant. We talked about Noether earlier and symmetries, but how does this invariant operate inside a number?
Lilien refers to this Q component as the closure charge.
Like an electrical charge.
Similar concept. If you think of a traditional particle having an electric charge, an NFN has a closure charge. This Q represents the foundational identity condition of the value. It is the mathematical answer to the most profound question you can ask about any complex system.
Which is what?
What must absolutely remain conserved for this quantity to remain itself?
What must remain conserved for this quantity to remain itself? Let that sink in for a second if you're listening.
It's a deep question.
If you put all 4 of these components together, the M, the D, the S, and the Q, you get the core revelation of this entire paper.
The true definition of the NFN.
An NFN is a number with closure memory. It remembers its own identity conditions. It stubbornly refuses to be a blurry, compressed GIF.
It holds tightly to its context.
And by giving a raw mathematical object a permanent identity condition, that Q component NFNs force us to do something quite uncomfortable, I think.
Yes, they do.
They force us to completely rethink what the word identity actually means in the realm of hard science.
It completely disrupts our standard definition.
Yes. Let's dive into that, because the paper introduces this beautiful, almost philosophical concept called closure ontology.
Closure ontology.
And it makes a bold claim: identity is not static sameness.
We have a deep psychological bias towards static sameness.
We really do.
We look at a granite rock and we say, that rock has an identity because it just sits there, unchanging for 1,000,000 years. We equate identity with immobility.
Right, if it doesn't move, it's a thing.
But in the biological, fluid, and quantum realities of the universe, absolutely nothing is immobile. Everything is constantly vibrating, exchanging energy, and morphing.
Everything is in motion.
So if identity isn't being perfectly static, what is it? Closure ontology defines identity as bounded persistence under transformation.
Bounded persistence under transformation. Think about your own human body for a second.
The ultimate example.
It really is. You are constantly shedding dead skin cells, millions of them a day.
Gross, but true.
Yeah, true. You're constantly breathing in new oxygen molecules and exhaling carbon dioxide. You're eating food, breaking down those molecular bonds, and rebuilding them into muscle and fat.
You're exchanging physical matter with the environment every single second of every day.
The physical atoms that are making up your heart and your brain right now are, in large part, completely different from the atoms that made up your body 10 years ago.
You are a ship of Theseus,
Yeah.
replacing your planks one by one.
Exactly. I am a biological ship of Theseus. Yet, despite this massive, ceaseless physical transformation, I am still me. You are still you.
We have a continuous, unbroken identity.
How? Because you are actively preserving an invariant structure, your Q component, your biological blueprint, your consciousness, across all of those massive physical transformations.
That is precisely what closure identity is. You aren't static. You are persistently transforming in a way that protects your core structure.
Which makes intuitive sense.
It does. And what Lilien has done, and this is the true genius of the paper, is map that abstract biological and philosophical concept into incredibly rigorous mathematics.
Because it's one thing to say it, it's another to prove it mathematically.
Right. He breaks this down into two formal definitions to make it mathematically usable. The first is closure equivalence.
How does math prove that I'm the same person I was yesterday?
The notation uses an equivalence symbol with a little serial subscript.
Okay.
It states that two completely different mathematical states are considered functionally identical if they preserve the same Q invariant under a transformation operator. We call that operator T.
So state 1 undergoes transformation T.
Maybe it ages a day, maybe it absorbs some heat, and it becomes state 2.
Right.
To a standard scalar number, state 1 and state 2 are different numbers. They are unequal.
Because the magnitude change.
Exactly. But to an NFN, if the underlying Q remained perfectly intact during that transformation, the system's identity held. The math treats them as equivalent in terms of their closure.
Wow. So the math finally recognizes the persistence of the structure, not just the raw counting of the atoms.
Yes.
That's huge.
It is. But Lilien goes further, because real systems don't just transform smoothly. They undergo stress.
They get pushed around.
They wiggle. They fluctuate. To account for this, he introduces the second definition: closure stability.
The wiggling boundary. The paper uses this epsilon symbol to define it.
Yes, the stability threshold is defined mathematically as epsilon.
What does epsilon actually do?
It formally dictates that a system's identity actually allows for fluctuation. A biological cell can endure osmotic stress. It can stretch, it can bend, it can adapt to a sudden temperature drop.
Without dying.
Right, provided that the total mathematical change falls within that designated boundary, that epsilon.
But if it stretches too far,
if the stress exceeds epsilon, the closure equivalence breaks violently.
the identity shatters.
The Q invariant is destroyed, and the identity is lost forever. The cell wall ruptures, and the cell dies.
Oh, man.
The hurricane hits a high-pressure shear and dissipates into a random breeze. The math can literally pinpoint the exact moment of death for a complex system.
It is stunning. It means our mathematics can finally handle systems that wiggle, morph, and adapt without breaking the equations.
Without just throwing in error code.
Right. We don't have to pretend the system is a static, rigid rock anymore to make the math work. We have a mathematical language for living, breathing, shifting reality.
Which is an incredible breakthrough, no doubt.
Yeah.
But it immediately introduces a massive, thorny problem.
Oh, right. Because if NFNs are these dynamic living numbers with deeply specific, stubborn identities, what actually happens when they bump into each other?
Exactly. How do you add or multiply a number that has a protective identity, a strict boundary scale, and a directional posture.
Because in the context-free world, if I add the number 2 and the number 3, I get 5.
Simple as that.
It's instantaneous, it's clean, and there is no friction. But if I try to mathematically add a molecular biological scale to a massive cosmological scale,
Right.
or an upstream current to a downstream current with totally different invariant structures, it feels like the math should just explode.
And in standard mathematics, it usually does, or it just outputs a completely nonsensical answer.
Like adding apples and supernovas.
Right, exactly. This is why Lilien had to invent NFN algebra. He established his incredibly strict rules of interaction.
Okay, what's the first rule?
The foundational rule of this new algebra is closure compatibility.
Closure compatibility.
You absolutely cannot just blindly smash two NFNs together and expect a clean output. Two NFNs can only interact, meaning they can only be added, subtracted, or multiplied if they share a common closure frame.
A shared closure frame, meaning they have to essentially speak the same underlying structural language before they are allowed to interact.
Think of it like organ transplantation in the human body.
Okay, good analogy.
You can't just take a kidney from person A and put it into person B. The biological closure frames have to match.
For blood types, the antigens, the tissue markers.
Exactly. If you attempt an operation, a physical one or a mathematical one, outside of a shared closure frame, the system violently rejects it.
It fights back.
In NFN algebra, if you try to multiply two incompatible numbers, the math literally blocks the operation by registering an infinite projection cost, or it triggers a total collapse of the NFN structure.
The math refuses to execute a lie.
That's a perfect way to put it. It refuses.
Okay, I am with you on compatibility, but I have to push back here, or at least get you to clarify something that really tripped me up in the reading.
Sure. What is it?
In standard math, multiplication is commutative. 2 times 3 is exactly the same as 3 times 2. The order doesn't matter at all.
Right. Classical commutativity.
But with NFNs, you have all these conditions and dependencies. What happens when the actual sequence of events, the order of operations, matters to the identity of the system?
It fundamentally changes the math. This is the principle of non-commutativity, and Lilien explicitly builds this into the architecture of NFN algebra.
Let me try to visualize this. Standard physics always uses the putting on your shoes and socks analogy.
Right, we've all heard that one.
If I put my socks on and then my shoes, I am fully dressed. I put my shoes on and then my socks, I look ridiculous. The order matters.
A classic, but a bit dry.
Yeah, I want a better analogy. Think about baking a cake or running a chemical reaction.
Okay, baking.
If I mix flour, sugar, and raw eggs in a bowl, and then I put that bowl into a 400-degree oven for an hour, my final identity state is a baked cake. The Q invariant is a stable, delicious dessert.
A highly irreversible transformation.
Very irreversible. But what if I reverse the order of operations?
Okay, let's see.
What if I put the flour, sugar, and raw eggs into a 400-degree oven in separate bowls for an hour, bake them, take them out, and then try to mix them together?
You'd have a mess.
My final state is not a cake. It's a bowl of hot dust and scorched egg.
Definitely not a cake.
The ingredients are exactly the same. The energy applied is exactly the same. But the sequence completely altered the final closure identity.
That is a brilliant way to conceptualize non-commutativity. In standard math, the sequence doesn't matter. But Lilien's paper formally states that n sub 1 multiplied by n sub 2 is not closure equivalent to n sub 2 multiplied by n sub 1.
The order is everything.
In the language of this framework, non-commutativity literally equals path-dependent closure. The specific sequence of events, the historical arrow of time and process, actively shapes and dictates the final identity.
So the system remembers how it got to its current state.
Yes, the history of the number is baked into the number.
Baked in, literally like the cake. It's incredible. And what is even crazier is that Lilien doesn't just stop at individual numbers interacting in a void.
No, he scales it up.
He scales this entire concept up into what he calls NFN fields. Let's try to visualize this for everyone listening. Imagine a standard vector field.
The classic example is a weather map on the local news showing wind currents.
Right. At every point on that map, there's a little arrow pointing in a specific direction showing how hard the wind is blowing.
It's just a flat grid of simple vectors.
Now, upgrade that entire map to an NFN field. At every single point in space, there isn't just a simple arrow.
It's much deeper.
There is a deeply complex 4-part closure coordinate node.
Picture it mentally. At every millimeter of space, there is a node dictating not just the value and the direction of the wind,
but concentric rings representing the specific scale of the turbulence.
And a dense, invariant core dictating the conserved identity of that specific storm cell.
It is a profoundly dense, layered map of physical reality.
And when these complex systems actually start moving through that space and time, they generate what the paper calls closure currents.
Closure currents. This is where we get into the fluid dynamics of identity, isn't it?
It is. When a system undergoes continuous transformation, like a river flowing down a mountain or a biological cell migrating across tissue.
Or a data packet moving through a neural network.
Yes. Its persistent identity literally flows through the system as a conserved current.
A literal current of identity.
Exactly. And this flow is governed by a strict continuity equation.
What does that equation say?
It dictates that the partial derivative of the closure current must equal 0.
Okay, partial derivative of the closure current equals 0. Let's translate that into physical reality for everyone. What does that mathematically guarantee?
It guarantees that identity doesn't just vanish into thin air.
It can't just evaporate.
Right. Even if there is massive local fluctuation, even if a single turbulent eddy in our river is shedding kinetic energy and churning violently.
Or a single cell is rapidly exchanging sodium and potassium ions.
The global closure identity of the system is strictly maintained in motion.
So the fundamental identity is not leaking out of the universe.
No, it is strictly conserved along the path of the flow. Local chaos does not imply global identity loss.
So we have these numbers interacting locally with strict rules, and we have them flowing as currents across complex fields. But that inevitably leads us to the next massive question.
How do they navigate?
Yeah, how does an NFN actually decide where to go? How does it choose its path through space and time?
And to answer that, Lilien essentially has to rewrite the entire concept of a straight line.
Which sounds impossible. A straight line is a straight line, right?
This is where the paper makes a stunning leap from algebra into Finsler-Noether geometry.
Okay, lay it on me.
To understand this shift, we have to look at how we currently measure space. In standard Einsteinian physics, or Riemannian geometry, space is defined by something called a metric tensor.
Think of it as the invisible grid paper that the universe is drawn on.
Perfect analogy. It dictates how distance behaves and how objects curve. In standard physics, this metric tensor depends entirely on your position.
Meaning the geometry of space is dictated just by where you are and what mass is nearby bending that space.
Correct. But the NFN metric tensor is vastly more complex.
How so?
It doesn't just depend on position. It permanently depends on position, D in your direction, and D, crucially, the invariant, the structure, the Q.
Position, direction, and identity. Let me make sure I'm grasping the magnitude of this.
It's big.
This implies that the very concept of distance, or the energetic cost required to move from point A to point B, is no longer just a cold geographic fact.
Not anymore.
The distance is actively governed by what the system is trying to preserve.
That is exactly what it means. The geometry of the universe bends to accommodate the survival of the invariant.
Wow.
And this completely alters the geodesic equation. In physics, a geodesic is defined as the absolute shortest physical path between 2 points in curved space.
A photon of light always travels on a geodesic?
Right. But the shortest physical path isn't always the smartest path, especially for a complex system.
Let's use an analogy here because this is where the paper gave me absolute chills.
The forest analogy.
Yes. Think about walking through a dense, wildly overgrown forest. Let's say point A is where you are currently standing, and point B is a safe cabin exactly 1 mile away.
Okay, got the picture.
The absolute shortest physical distance, the standard mathematically pure geodesic, might require you to walk in a perfectly straight line that goes directly through a massive, impenetrable patch of razor-sharp briars, thorns, and toxic plants.
A path that, while geometrically the shortest, would result in your physical destruction.
Exactly. If you blindly walk that straight line, you get shredded to pieces. You don't make it to the cabin.
The system dies.
But if you are an NFN system, you aren't just a blind point on a graph. You have an invariant condition, a Q.
A closure charge.
Let's say your Q is your biological imperative. Do not bleed to death. Maintain structural biological integrity.
A very strong imperative.
Under NFN geometry, your true geodesic, your mathematically ideal and natural path is absolutely not the straight line through the thorns.
Well, it curves.
Your mathematically ideal path is the curved, winding, physically longer path that carefully navigates around the briar patch to protect your Q.
Lilien formalizes this as the least closure disruption principle.
The least closure disruption principle.
It is a profound evolution of physics. The modified NFN geodesic equation introduces an entirely new mathematical term, a repulsion variable dependent on Q.
A repulsion variable.
That term acts as an active mathematical force that literally repels the trajectory away from paths that would destroy the system's closure.
It introduces a friction against death.
It forces the mathematical trajectory to protect the identity.
That's incredible. Complex systems, living systems, turbulent systems, they don't just blindly seek the shortest energetic path like a rock rolling down a hill.
Right, they aren't rocks.
They seek the path that minimizes disruption to their closure. They actively navigate the geometry of their environment in order to survive.
It is like the mathematics finally has a survival instinct built directly into the geometry.
It's just unbelievably elegant, and the best part is that this isn't just a beautiful theoretical sandbox.
No, not at all.
Lilien didn't just write this to flex his mathematical muscles. He built this to solve deeply confusing mysteries that are currently baffling scientists across entirely different fields.
Real-world mysteries.
Yes, and that brings us to the real meat of the paper. The domains of application. Let's start where we've been naturally hovering this whole time. Biological boundaries.
Biology is undeniably the ultimate perfect domain for Noetherian Finsler numbers.
Why is that?
Well, as we've been discussing, living systems are never, ever just magnitudes. Every single biological value, every chemical gradient, every electrical pulse has a strict boundary, a specific scale of operation, and an overarching identity to protect.
Which sounds exactly like an NFN.
Exactly. The paper outlines a deeply specific mathematical model for membrane flux.
The movement of materials in and out of a cell.
Yes. Think about a biological cell membrane. Historically, mathematical models have treated the membrane as a relatively passive, porous spatial surface.
Like a microscopic screen door. Things bump into it, and if they are small enough, they just slip through the screen.
But the NFN model completely rewrites that.
How does it treat it?
It treats the cell membrane not as a passive screen door, but as an active, highly intelligent boundary closure operator.
A boundary closure operator.
Precisely. The equation for the flux specifically binds the raw magnitude of the chemicals moving, the physical vector direction across the membrane, the localized scale of the membrane itself, and, crucially, the conserved cellular identity, the Q subcell.
So what does that actually look like in practice, if I'm watching a cell do this?
It means the membrane is mathematically filtering that flux specifically to preserve the Q invariant. It is a smart firewall.
Oh, a firewall.
Yes. If a beneficial nutrient approaches, the membrane's mathematical geometry opens up because that flux supports the Q condition.
It recognizes the nutrient is good for survival.
But if a highly destructive toxin tries to enter, the membrane actively resists. The geometry changes. The NFN math describes the biological intent of the boundary, not just the physical geometry of the holes in the wall.
It mathematically codifies the immune response at the boundary layer.
Yes, it does.
That alone is worth a Nobel Prize in biology, honestly. But Lilien doesn't stop at biology.
He goes much deeper.
He takes this exact same mathematical framework and applies it to the most fundamentally strange level of reality we know of, quantum coherence.
Quantum mechanics. The realm where all intuition goes to die.
It really is weird. Particles being in two places at once, wave functions collapsing when you look at them. It's a mess. But NFNs seem to offer an incredibly clarifying lens for the chaos.
They do. In standard quantum mechanics, treating a probability amplitude, the likelihood of finding a particle in a specific state, as a simple, context-free scalar value is a known, acknowledged, incomplete projection.
We know we're missing something.
We know we are losing information. An amplitude simply cannot be detached from its phase, the specific macroscopic regime in which it's being measured, or the underlying symmetries of the quantum system.
So Lilien defines a completely new object, a quantum NFN.
A quantum NFN.
It mathematically binds the amplitude, the phase angle, the measurement scale, and the conserved identity of the quantum state into a single unbreakable closure coordinate.
And this is vital. Lilien is very careful to state that this does not replace standard Hilbert space math.
We aren't throwing out the Schrödinger equation.
No, not at all. Instead, the NFN framework wraps around standard quantum math. It provides a tracking mechanism.
Tracking what exactly?
By monitoring that Q invariant against the chaos of the surrounding environment, NFNs can track exactly how coherent quantum states manage to survive shifting symmetries.
So it measures survival.
It gives us a formal mathematical language to predict exactly how long a quantum state can persist before it decoheres and collapses back into classical reality.
It's mathematically mapping the survival of the quantum state. It's tracking the ghost in the machine.
That's a great way to put it.
And then, As if unifying biology and quantum mechanics wasn't enough, he zooms all the way out to massive macrophysics, turbulence dynamics.
We were talking about flowing water, deep ocean currents, atmospheric weather systems, the jet stream.
Now, to the naked human eye, a turbulent river or a hurricane just looks like pure, violent, unpredictable chaos. It looks like the absence of math.
It looks totally random. But physicists know it isn't pure disorder. Turbulence is actually highly structured.
It's just structured in a way that our standard equations struggle to hold on to without blowing up to infinity.
Exactly. Lilien beautifully describes turbulence using NFNs as partial closure under scale transfer instability.
Partial closure under scale transfer instability. Absolutely love that phrase. It sounds like poetry.
It is very descriptive.
But let's break down the mechanics of what that actually means. What is a scale transfer instability?
In any turbulent system, you have large structures, say massive swirling eddies of fluid in a river.
Okay, large whirlpools.
Those large eddies become unstable, and they physically break down into smaller eddies.
Right.
Those smaller eddies become unstable and break down into even microscopic eddies. This process transfers the kinetic energy of the water all the way down the scale ladder until it finally dissipates into the environment as microscopic heat.
And that entire process is called the cascade.
Yes, the turbulent cascade.
So the physical water is churning chaotically, and the eddies are constantly dying and being reborn at different sizes.
Exactly. The physical matter is in chaos. But the rate of that energy transfer, the mathematical architecture of the cascade itself, is a stubborn, beautiful invariant.
Wait, really?
Yes, that cascade structure is the Q invariant of the river.
Oh, wow.
The NFN tracks how the massive energy of the river scales down through a dozen different physical regimes while stubbornly, flawlessly preserving that overall cascade structure.
It's the mathematical tool for finding the deep underlying order inside the violent chaos.
Finding the order inside the chaos.
And that leads us to the final domain of application in the paper, and honestly, the one that might be the most immediately commercially relevant to our current world right now. Invariant-aware artificial intelligence.
We are firmly in the age of deep learning and massive multi-billion parameter neural networks.
AI is literally everywhere right now.
But standard AI models, as powerful as they are, have a fundamental structural limitation in how they represent data.
Yes, let's explore this deeply, because this S-curve of AI development is what everyone is talking about. How do standard AI embeddings, the way an AI actually visualizes and stores concepts, how do they work right now, and why do they fail?
Well, standard AI embeddings map the world by asking a very basic, purely geometric question. What is close to what in a massive, high-dimensional data space?
Proximity.
Right. If you feed an AI millions of pictures, it processes the pixels and realizes that the data for an apple is geometrically very close to the data for a cherry.
So it groups them together in its mind as red fruit.
Exactly. It is entirely based on pattern proximity.
But proximity has limits. This is why AI image generators still hallucinate weird things, right?
Yes, the hallucination problem.
If I show a standard AI a picture of a coffee mug sitting perfectly upright on a table, it knows it's a mug.
Sure, it's seen a million upright mugs.
But if I take that exact same coffee mug, turn it completely upside down, smash it flat with a hammer, and change the lighting, the AI looks at it and says, that is a Frisbee, or that is a piece of modern art.
It completely loses the concept of the mug.
Because the raw pixels, the geometry moved too far away in the beta space. It lacks object permanence.
That is exactly the failure point.
Yeah.
The AI doesn't understand what the object actually is. It only understands what the object currently looks like compared to other static pictures.
Right.
But an NFN-based AI architecture asks a profoundly different question. It doesn't just ask what is close to what.
It asks the closure question.
Yes, what fundamentally persists under transformation.
So how does an NFN embedding actually change the AI's brain?
An NFN representation explicitly forces the neural network to separate the data into our four components.
M, D, S, and Q.
Right. It distinguishes the raw magnitude of a visual feature, the directional orientation of the object, the scale of its relevance, and, most importantly, its invariant identity.
The Q.
It provides a formal mathematical tool for representation learning, where the state of the object is completely inseparable from its physical constraints.
So if I show the NFN AI the smashed upside-down coffee mug, it doesn't just look at the raw pixels.
No, it runs a transformation equation.
It says, okay, The spatial scale changed, the directional orientation flipped 180 degrees, but the underlying topological structure of a container with a handle, the Q invariant, persisted through the transformation.
Exactly.
It looks at the smashed ceramic and correctly says, that is a coffee mug that has undergone catastrophic stress.
Exactly. It allows the AI to learn the actual rules of physical reality,
Yeah.
the invariants of the universe,
Mm-hmm.
rather than just blindly memorizing massive static patterns of pixel proximity.
That is a massive paradigm shift.
It teaches the artificial intelligence not just what things look like, but how things survive, persist, and react as they change. It is giving AI a true sense of object permanence on a structural mathematical level.
It's a massive leap forward in machine cognition, a machine that understands persistence.
Yes.
Which is a perfect concept to bring us to the end of this incredible deep dive into the calculus of closure memory.
We've covered a lot of ground today.
We have covered a truly staggering amount of ground, from the flow of rivers to the synapses of an AI. Let's synthesize all of this for you listening.
Okay, synthesis.
What Philip Lilien has actually achieved with Noetherian Finsler numbers is not a rejection of the mathematics that built our modern world.
He hasn't arrogantly thrown away the scalar or the vector or the Einsteinian tensor.
He's done something much harder. He has completed them.
He really has. He has provided a rigorous, beautiful mathematical home for all the incredibly complex systems that simply refuse to be stripped of their context.
Systems that are messy, direction-dependent, violently multiscalar, and constantly transforming.
Systems that have a deep structural memory.
Systems with scale and posture and a stubborn, built-in desire to preserve their unique identity in a chaotic, entropic universe. NFNs give us the mathematical vocabulary to finally describe the persistent survival of reality.
And stepping back from the math for just a moment, understanding this architecture raises an incredibly important question, a deeply provocative one to end on, I think.
Okay, let's hear it.
If our mathematics can now formally, rigorously encode memory and identity persistence at a fundamental structural level through these NFN fields,
Right.
could the physical structure of human consciousness itself be mapped as a incredibly complex topological NFN?
Oh, wow. I need you to elaborate on that because that is a massive thought.
Well, think about it. Our brains are essentially massive, anisotropic, multiscalar environments.
Highly complex, constantly shifting.
What if human memories, our unbroken sense of a continuous self, the very persistence of our own ego, day after day? What if these aren't just abstract psychological concepts?
What are they then?
What if consciousness is literally a macro-scale closure current flowing through the complex shifting geometry of the brain's neural network?
You're saying consciousness is an invariant.
Are we, as conscious beings, simply intricate NFN fields fighting every single second of our lives to stubbornly preserve our unique Q invariant against the relentless dissolving noise of time and entropy?
Or are we just a biological mathematics navigating the path of least closure disruption?
That's the question.
That is. Man, that is a thought that is going to linger with me for a very, very long time.
Me too.
It brings us right back to where we started this whole conversation. When you look at an old photograph, or when you hold those 5 perfectly smooth stones in your hand, you are looking at a clean, static snapshot.
You're looking at a comforting abstraction.
But the reality, the biological tissue constantly healing and regenerating around the bones in your hand, the chaotic fluid dynamics in the atmosphere around you, the very consciousness actively perceiving those stones.
That messy, beautiful reality is an NFN.
It is a physical value that remembers exactly what it is, where it came from, and exactly what it has to do to survive the journey.
It is so much more than just a number. It is a number with a memory.
Thank you so much for joining us on this incredible journey. Keep questioning the abstractions, look for the invariants in your own life, and we will see you on the next deep dive.